Hello, welcome to Math Musings channel. Today we will consider fractions, and we all learned fractions in school. We think we know about them everything, but this is not the case. Please stay and look at this video, and I promise you will be surprised. Let's move on and start from introduction. Let's begin with a fraction multiplication operation. So we'll consider axis where I want to put numbers we are going to play with. So in the middle of this axis I will put 1, then there will be 2, 3, 4, and so on, natural numbers. On the other side I will put 1/2, then I will put 1/3, then I will put 1/4, and so on. The reason I put them this way and not the way we see them in a standard situation is that this image is better corresponds to algebraic structure. So multiplication operation, I will denote it with either star or just dot, works like this. If I 1 multiply by 1, I want to get 1, that's standard. If I multiply 2 by 1/2, I will get 1. In general, if I multiply number n on 1/n, I will get 1. So 1 is playing identity role, and the multiplication of fractions work like this. Plus, I want to consider system where just for each of numbers like larger than 1, I just use regular multiplication operation, so it will be 6, for example. And if I multiply fractions like this, I will get just standard result, 1/6. So what we can see here is that we have algebraically, in terms of multiplication operation, complete symmetry between numbers on the right of this axis and numbers on the left of this axis. So this symmetry also can be expressed so that if I change each n to 1/n, and I change each 1/m to m, you will not notice. So there's just complete symmetry here. So now let's move on and consider addition operation. Let's start from 1 plus 1. What can be easier, right? If I add 1 plus 1, usually I would write here 2. And that's just like standard result. But hold on, why do we break in symmetry here? So if we allow 1 plus 1 equal 2, and we can build all our standard system with addition and multiplication, when we should be able to do the same using 1 plus 1 equal 1/2, right? Because of the symmetry, it will be completely the same system, but like mirrored. So why do we prefer 2, and why not 1/2? If 1 is like, you say 1 is some special element, it's identity, multiplication identity, probably for other numbers we have something more reasonable. So let's say consider 2 plus 1/2. Let me write this as 2/1 plus 1/2. Okay, so usually we would do something like 4/2 plus 1/2, and that's 5/2, right? So, but why do we use this rule that we need a common denominator here, like here and here, right? So we have exactly same rights to do it the other way around. So we can say that we want to have a shared numerator instead of denominator. Okay, so let's see. So we will get 2/1 plus 2/4. And then we just have common numerator, and we have 2/5. So again, we have here full symmetry. So if right hand side legitimate, then we should accept that left hand side also legitimate. So then we kind of need to admit that 2/5 can be 5/2, and then we kind of don't have a conflict here between left and right side. But then, like, our system collapses. Instead of just left and right hand side on our axis, we just have like only 1/2 of the line, and the rest is the same. So we don't want this. So let's first play a little bit with this alternative, like mirrored system, and try to think how we can combine these two into non-contradictory system. Okay, so let's move on and consider this table. Here on the left I will use just our standard addition operation. On the right half I will use a mirrored situation. So if we have in standard situation 1 + 1 = 2, like here it's totally understandable. On the left side we should have 1 + 1 = 1/2 to make it equivalent. Okay, if on left hand side we have 1/2 + 1/2 = 1, then here we have to get something different, right? So here we have, let me check, so here we'll have a shared numerator 1, and we will have a sum of denominators, so it's 2 + 2, so it will be 1/4. So another example, 4 + 4 + 4 + 4, just 16. In a mirrored system, 4 + 4 + 4 + 4 will be equal, you should consider it as 4/1 and so on, plus 4/1, and we use the rule that we care about common numerator and we sum up all denominators. So this will be equal to 4/4, which is 1. And last example is when we have like 4 quarters = 1 in a standard situation. Here we will have what? We will have common numerator is 1, and here we will have a lot of 4s summed up, right? So we'll get 1/16 here. So just that's a little bit of practice just to get used to it, and I want to show you a general rule. So the general rule will be here. If we have like a fraction m/n plus, let's say, p/q, here we would prefer to have common denominator, right? So we'll have nq, and here just nq plus np, right? So on the right hand side we would have a different result. It will be, we will want to have common numerator, so we will have m multiplied by p on the top, and on the bottom we will have np plus mq. Okay, so let's move on with this system. Let's consider distributive law. We know that distributive law, sorry, so what I forgot to say is that to disambiguate right and left hand side, I will use two different notation for plus operation, okay? So here I will use plus with hat on top, just our regular plus operation. On the right I will use plus with hat on the bottom, like this. So it will be plus operation that follows these rules on the right hand side. With this, let's proceed to the next slide. Distributive law. We know that it works for standard plus operation. Let's just double check one example that it works also for our unusual plus operation. So we start from this, and here on the right I first open parentheses to do multiplication operation first and then addition. So I proceed to this, and finally I get the output 6. You can just verify that that's true. So on the left hand side I can first sum what is inside the parentheses, this part. It will be 6 over 5, and then I multiply by 5 and I get 6 again. So in general it will be the case that distributive law like this just works fine for our new addition operation. So let's consider another example. Let's say I want to compute what is 2 plus 3, just like non-standard plus, multiplied by 2 plus 3 with the standard plus operation. So what we do in this case, how we open parentheses in this case. So here what we can do is just notice that this can be computed and become just one number. When it's just one number, we can just open parentheses, same way as we did here. Okay, so then this will go to multiply with 2, and it will go to multiply with 3. On the other side, what I can do, I can think of this one as a number, and then it will go into parentheses to multiply with 2, and it will go to multiply with 3. So in case of red errors, I will get something like this. I will get 2 plus 3 multiplied by 2, and then plus 2 plus 3 multiplied by 3. In case of blue error, I will get something different. I will get 2 plus 3 multiplied by 2 and plus 2 plus 3 multiplied by 3. Notice the symmetry here, how we change the plus operation that stand in the parentheses here on the here and here, and what we have here and here. So if we open these parentheses now, because we know the distribution law work for this case and for this case, if we open these, we will notice that it is equal 6, and this one also equals 6. So one thing to notice here is that it is generally the case that n plus m multiplied by n plus m will be always equal to n multiplied by m. That's the way we open parentheses. And in the case of different numbers, like n plus m multiplied by p plus q. We can just follow the rule that I described here and either go this way or go this way. So there will be two different ways to open parentheses here, with either this sign in the middle or with this plus in the middle. Okay, so this is kind of a new type of distributive law. It is somehow unusual, but let's move on to another topic now. So let's observe something that I call duality, and to do this, let's compute these values. I denote a number with a minus sign on top. It's just a notation for 1 over n. So let's see what we get for all these expressions here. 2 plus 3, just standard plus is 5, and minus give us 1 over 5. Here on the bottom we care about same numerator, so 1 here and 1 here. We are good, so we have 1 and 5 at the bottom. Okay, so let's check what is on the right. 2 plus 3. 2 plus 3 is like 2 over 1 plus 3 over 1, right? And to the power minus, it is equal, we should get the common numerator, that will be 6, and on the bottom we will get 3 plus 2 is 5. So it's equal 6 over 5 with a minus, and that will be 5 over 6. Okay, so let's check what is in the last case. Last case will give just our standard fractions addition rule, and we will get 5 over 6. So what we can notice here, something interesting. So we can notice here that n plus m to the power minus is equal to n minus plus m minus. That's the same as 1 over n plus 1 over m. Okay, so we can kind of take this minus on the power and put it inside the parentheses. And same happens on the left, on the right. If we have n plus m to the minus, it will be equal to 1 over n, just regular plus 1 over m. So we see that minus is like the operation of taking inverse works like isomorphism between two of our operation, the operation of like dual plus and just operation of standard plus. We saw this in another field of mathematics that you can like recognize as, if we take not of x and y, you will get something like not x or not y, right? So there is a rule like this, and not of x or y is the same as not x and not y. But this is only working for x and y either true or false, like two values here that play this game. In our case, we have a full range of numbers, natural numbers, 1, 2, 3, etc. And we have a full range of corresponding fractions, 1/2, 1/3, and so on. And all these numbers will play this game with these operations that we introduced, these like dual plus and just direct plus. Okay, so what's the conclusion? What we get? We got like numbers in form of fractions, so I can clearly write 1 as 1 over 1, 2 as 2 over 1, and 1 over 2, and then 3 over 1, and 1 over 3, and so on. So we have completely like symmetric numbers. We have a multiplication operation with identity element 1. We have two completely equivalent additions that work simultaneously on this system. We get associative, commutative, and distributive law working, and we got this like duality, a complete symmetry in our system. So we don't need to choose which of the sides we prefer. And the one small note with associativity is that each operation in isolation, like plus operation, will be associative, and dual plus will be associative. But they do not, we cannot mix them with each other. They kind of have same priority, but the order matters. So it is expressed here. Then we need to put parentheses in order to define the operation execution order. Okay, so final question is of course application. Where we can see this. It's clearly that 2 plus 2 plus 2 equals 6 is used everywhere, right? We know how to use it. But what about this one? So this is just great. What about this one? Can you think of the cases where this is used? Please put video on hold. I promise you that you learned this case, you know this example, and you learn it at school. Try to recall what is it. I give you a couple of seconds to recall. So now let me just answer this question. So let's turn to electrical circuits, where we have elements such as resistors, okay? So when we have a resistor R1 and we have a resistor R2, then the total resistance of this segment of circuit will be equal R1 plus R2. There is another way to connect these two resistors, right? This is a parallel connection. But if we take this is not a parallel, this is serial. Yeah? If we take the parallel connection, R1 and R2, like this. So the total, let me just write here R total. So the total here will be equal, you can look out the formulas, but it will equal R1, R2 divided by R1 plus R2. And this is exactly equal to R1 plus R2. So our new plus that we just invented, completely symmetric to our standard plus, it's reflect the situation of adding resistance in parallel connections. And if you check like there are other elements of electrical circuits that behave same way. For example, you can check how let's say capacity, right? If you have two capacitors connected in serial way, then their total capacity will be C1 plus C2, and their parallel capacity, let me write here like serial C parallel okay, C parallel will be C1 plus C2. And pretty much similar situation with inductions and coils. Okay, so that's the one example of application. We now have like numbers that describe parallel and serial connections of elements. If you know other examples where this dual plus operation is used, let me know in the comments. That's it for today. I hope you enjoyed this video and found something very surprising. Have a good day. This was channel Akko Math Musings, and see you next time. Thank you.